So we're going to continue on with some impulse momentum theorem. So this is where we're relating impulses and momentums together. So a bullet is accelerated on the barrel of a gun by hot gases produced by the combustion of gunpowder. What is the average force exerted on a 0.03 kilogram bullet to accelerate it to a speed of 600 meters per second in a time of 2 milliseconds? Okay, so this is the idea of, we usually separate F delta t is equal to m delta v. This is the key part of impulse momentum. It's not really something new. It's just a different way to formulate Newton's second law. Okay, and it's a convenient way to discuss it or to do analysis on it. So here they're asking what the average force is. Well, I would just rearrange this delta v over delta t, and the average force would be the mass. It is a 0.03 kilogram. The delta v, which is the change in velocity, is it's starting from rest and it's going to 600 meters per second. So I'm going to multiply by 600 meters per second. I'm going to divide by the time, which is 2 times 10 to the minus 3 seconds, because it's in milliseconds. So you got to be careful on the unit sometimes. I get 9,000 newtons. A person slaps her leg with her hand, bringing her hand to a rest in 2.5 milliseconds from an initial speed of 4 milliseconds. So the delta t is 2.5 milliseconds, and the initial speed was 4 milliseconds, 4 meters per second. What is the average force exerted on the leg? So F is equal to m delta v over delta t, right? Because that's the impulse momentum formula. The mass was 1.5 kilogram. The change in velocity, it goes from v naught to rest. So we say 4 meters per second. Again, you could say negative 4. In this case, it doesn't really matter what you mean by positive or negative force. That just indicates direction. 2.5 times 10 to the minus 3 seconds for the denominator here for t. And so I just multiply that. 1.4 times 4 divided by 2.5 e minus 3. 2,400 newtons. B, would the force be any different if the woman clapped her hands together at the same speed and brought them to rest in the same time? No. Because if she was moving both hands at the same velocity, the change in velocity would actually be twice. Well, I guess the momentum on one hand would be the same. So I guess you would say yes. I was going to say the total momentum would be 0, but the only thing that affects the force is the mass, the change in velocity, and the change in time. So as long as all of those quantities are the same, then they ought to be the same. Suppose a child drives a bumper car head-on into the side of a rail, which exerts a force of 4,000 newtons on the car for 0.2 seconds. What is the impulse imparted by this force? Okay, impulse is given by F delta t. So that's a force times the time, 4,000 newtons times 0.2 seconds. And that would be, what, 800 newton seconds. Find the final velocity of the bumper car if its initial velocity was 2.8 meters per second and the car plus driver mass of 200 kilograms. So this impulse, F delta t, is equal to m delta v. And so delta v would be the impulse, which is 800 newton seconds, divided by the total mass of the object that's changing its velocity. And that's 4 meters per second. So the delta v is 4 meters per second. Now, you have to remember which direction the delta v is. This is just simply the change in velocity is going to be 4 meters per second. Is it positive, negative? If they were originally going 2.8 meters per second like this, it's probably pushing against them to go this way. So they're going to have a delta v of 4 meters per second going the other way. So its final velocity will be 2.8 minus 4, or would be, you could say, negative 1.2 meters per second. Or, yeah, so we would say 1.2 meters per second in the other direction. Okay. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.